can use the Markov inequality later. And then I got this a square plus expectation of x and identity x greater than or equals to a. So this one is greater than or equals to a square plus expectation of a identity expectation identity of x greater than or equals to a, because the line here from the graph here we can see a times identity function will always be greater, x times identity will always be greater than a times identity. And then this one, we can bring the a out and the expectation becomes probability. So I used, since x is uniformly distributed, so this is the answer, and then I get the expectation of maximum a x is greater than or equals to a squared plus 4. And then for question 4, we just have to show whether the expectation is greater than this. So from question 3, we can see that expectation of maximum of ax is this, always greater than this. But for maximum of a and expectation of x, we can see that it will be a if a is greater than 4, since our expectation of x from question B is 4, and it will be 4 if a is less than 4. So this thing will always, the maximum it can go is either a or 4, but expectation of maximum ax can go up to a squared plus 4. So from there we can conclude that expectation of this is greater than or equals to this. It can go up to equal or even more. That's all.
Okay, Sudha, thank you. So can you go back to the beginning? Okay. Just a minute. Let me try something. Let me see if I can annotate the screen. Share screen. Oh, strange, huh? I can't annotate the screen. Options. Oh, okay. I can annotate this. Okay. Okay, so basically this is okay, yeah, I was trying to annotate the screen. So basically the geometry is like this, right? Okay, because you're taking every pair, you're looking at the maximum, right? So the max, so the maximum can either be 1, 2, 3, 4, 5, or 6. So you have for 1, the only way you can get 1 is this point, right? So there's only one outcome. You get 2 for these points, right? There are 3. So the geometry is very interesting, right? So it's 1, this is 1, 2, 3, this is 1, 2, 3, 4, 5. So it's 1, 3, 5, 7, 9, 11, right? So basically then you multiply with 1 over 36 because that's the, basically this is the, all pairs are equally possible. And then basically this 1, 3, and all that is basically just counting, all right? You're counting how many you have, that's all, okay? So it's okay, well, if you want to write it like this, it's also okay. This is kind of like a more, kind of like in a formula style, huh? Okay, so this is okay. Can you scroll down? Okay, that's okay. So up to this point, so basically you don't round like this, okay? You basically just you just leave it in fractions, something, okay?
Okay, doctor.
I mean, yeah, don't round it like this, all right? Because once you round it, well, it's not a final answer, right? Because if you want to use it for further work, you shouldn't round it, yeah, because you will introduce truncation error. So you better just leave it in the form of the fraction here. That will do, all right? Okay, but that's correct lah. You basically just do this algebra work, and then can you scroll down? Scroll down. Okay, okay, okay. A bit up, a bit up. So okay, up to this point, okay, all right. But then starting from here, this is what's going on here? Let me see. Why would, for example, right? Why would here? Why would px less than or equals to a equals to a? Why would it be?
Because I thought it's the area under the graph
No,
for
no,
the identity function.
no. And it's not an identity function. It's an indicator function. It's called an indicator function. Yeah.
Sorry, yeah. I thought it's the area under the indicator function graph.
No, so you look at it carefully. This x is a random variable, right? That's already defined, right? Yeah. So your x is it's a uniform random variable for it's uniform, right?
Yes.
Okay. So in your a is any arbitrary constant. Yeah. Correct.
Yes, doctor.
So how can it be equal to a? Let's say, for example, if your a is 5, can it be 5?
Oh, it's always 1/6.
Yeah. So I think there's some problems of you using this kind of. There's something wrong with the idea here, right? So basically, this is all. There are problems here, right? So okay, so what you do is you basically only have up to this point. Okay. So up to this point, what you can do is this will be a times. So that will be a over 6, right? Well, actually, not really. It's not really a over 6. Let me see. Let me erase this. It will depend on what a is. Okay. It will be something like this. It will be the so this part here will be the minimum of a 6 over 6. Okay, agree? You look at this carefully. So this minimum A6 means if your A is larger than 6, right, then automatically, so you will get like, for example, something like this. This is definitely 1, right? Because your X is definitely less than, less or equals to 6, right? So anything larger than that is definitely still equal to 1, isn't it?
Yes.
Right? Because your x is surely less than or equals to 7, right? Of course, it can't take 7, but the probability that it is less than 7 is definitely 1, yeah? So that's why over here, you can pick, if if your a is less than 6, then you take a. Otherwise, you take 6, which is 6 over 6, you get 1, right? So over here, you get this part. And how about this part? So this part is basically you sum your x, right? So this is sum of x times the mean, so 1 over 6. Your x is starting from a, is it? Uh,
Greater than A, doctor.
okay, greater. So this will be larger than a. So So larger than A. All right. So you basically have this sum, right? Okay. So is there anything that you can say about this sum? So this sum will be equal to suppose if your A is larger than 6, this sum will be 0, right? Agree? Because if your x cannot be, so basically your x cannot be larger than 6. I mean, like this one is basically like the case where you have 0 elsewhere, right? This means x outside of 1, 2, 3 until 6, right? So over here, so this will be basically we are talking about your sorry, the A. Okay, so you need to think about what this sum actually is. So for example, let's say, let's try some examples. Let's say if your A is 1, what will happen? So basically, if your A is 1, you will find this sum, right? X over 6, x from 2 until 6, right? Agree? So basically, this is you add 2 all the way until 6, right? 2 plus 3 plus 4 until 6, and divide by 6. Okay. Similarly, if your A is equal to 2, your sum will be starting from larger than 2. So it will start from 3 and go to 6, right? 6. So this will be 3 plus 4 plus 5 plus 6 over 6. Okay. So now generally you will need, so basically generally then you know that from this consideration that you can say that sum of this is basically so this is A, so the next one will be A plus 1, right? A plus 1 plus A plus 2 plus all the way until you get 6, right? Okay. All right, provided that your A is actually between, actually your A can also work. So between 6. I said A is so A is already positive, right? So yeah, for your A between 0 and 6, you will have this thing, right? Otherwise, outside of that, if your A is more than 6, then basically this thing is 0. Okay, because when your A is 6, basically your X cannot go out of 6, right? So this mass will be 0. Okay. Okay. So you check back the solution later, yeah, on this part. All right, Sutha.
Okay, doctor.
Okay. Let's scroll down. Okay. The last part here, basically, you just apply Jensen's inequality. Okay, because so this one you just say that by Jensen, you just need to say that the max function, right? The max function is convex. So that's all, right? Because the max function basically is So over here you have either A or X. So your X basically is I mean, like for the continuous case, it's like this. Your constant is maybe something like this, right? So your max of AX is basically this. Okay. And this function is basically a convex function, right? Because you can put any line to a line across it, and you'll find that anything below this straight line, all right, this curve here, the prediction is less than the straight line. Okay, so this is a case of a convex function. So you can just invoke Jensen's inequality, all right?
Okay, doctor.
Of course, in your case here, your x is really not smooth like this. It because your x is discrete, right? So your but then nonetheless your x is something like this. It's like a step function. Okay, the step function. All right, but then it's actually just a special case of your continuous function here. It's slightly different, but it is still convex, right? Okay, so you can apply Jensen's inequality. Okay. Okay, thank you, Sudha.
Thank you, doctor.
Okay, next person, next question. Question 2.
It's me. Let me share my screen.
Hi. Let's share your screen.
Can you see it?
Yes.
Okay. Okay, so this is the question. We have random variable x equal to exponent of mu plus sigma z, and it's known to have a log normal distribution. That means that log x is normally distributed with mean mu and variance sigma squared. So the first question is, using Jensen's inequality, show that the expectation of x is um, uh, more equal than expectation of exponent mu. So we have this first. Yeah. So I asked if this is the expectation of x, and we know that expectation of x is equal to expectation of exponential log x. A simple math. So I did these steps, and then I got the expectation from the Jensen's inequality, since f is convex, and here f is exponent of mu plus sigma z, and we get the expression. Okay.
Just continue.
All right. So the second one is just to verify the inequality by evaluating it, and I got the same. And for question C, if we have x1 to xn, they're identical and independently distributed log normal random variables with the parameters mu and sigma squared, show that this expression is true. I tried doing it, but I couldn't really complete it. At first, I thought I can use the Jensen's inequality, but then I tried doing it and I couldn't find this last expression. And then I tried doing the Markov inequality, but the same thing happened. So I just stopped at this, and I'm not sure how to do it.
Okay, it's okay. Let's go back to the first part. Okay, the question says, let's look at the question again. Using Jensen's inequality, show that the expectation of x is, okay, right. So you use the log, you start with the log of x. Okay. Right. So let me annotate it. Okay. So let's say, so the log function, right, is convex or concave?
It's convex.
The log function is like this. So is it convex or concave?
Concave.
It's concave, right?
Yeah.
Okay. So the convex case, you have if you put a secant line on it, so the values on the curve, they are actually less than the values on the straight line. But this is kind of like the reverse, right? So it's the opposite. It's a concave function, right? So for concave function, your Jensen's inequality will reverse, right?
But for I wasn't thinking about log to be honest, because in this inequality it's gonna be exponential of something, and exponential of something is convex, right?
Okay, let me just continue with the idea here first.
Okay.
So you have so basically you have this is the case for Jensen's, right? Jensen's equality for convex function, right? So if it's concave function, it will reverse, right?
Yes.
So over here, so your so you start with this. So the expectation of log x is this form, right? So definitely you know that this is actually less than or equals to the log of ex, right?
Yes.
So since it's log normal, so log x is normal, right? With mu, right? Mean mu, right?
Yes.
And therefore, basically, you rearrange, you get this. Okay.
Oh, okay.
Okay. Now let's look at your working. So you start with this. You write like this. Okay. And then somehow you wrote x to be e of mu plus sigma z. All right. Now let's look back at the question.
Oh, wait.
Okay. Where your x is equal to, okay, fine. Okay, fine. Okay, so this is correct. Okay. And then okay, then this basically cancels, so you get this. Okay. Then you get the expectation of the expo. Okay, so here you are using the you're basically using the Jensen's inequality for a convex function, right?
Yes.
Exponential function is the exponential function is going out like this, so it's a convex function. It's a convex function.
Yes.
Sorry, let me see. Is it convex?
Yes, it is.
Okay, all right. It's convex function. Okay. So it's convex. So you can use this. So this equality is true by Jensen's inequality. Okay. Then so this is a constant, right? So yeah. So yeah, correct. Yeah. So since expectation of z is 0, isn't it?
Yeah.
Z is normal 0, 1. So okay. You can also do like this.
Yeah. Okay.
I'm actually there are two ways to do this problem. Yeah. Okay.
Okay.
I'm showing one so it's okay. Yeah. If you are able to see that you can express x as e of log x, right? That this will also work. Okay.
Okay.
Okay. Great. Then what was the second part?
The second part is just to prove it without using the Jensen's, just evaluate it.
Oh, okay. That already done, right?
Yeah. And then the last question is the one that I couldn't do. This one. C.
Okay. Right, it's okay. So let me handle the C. So let's look at B again. To be clear, so expectation of x.
I'm not sure of the second notation. Should I just directly say this from this to this one?
Well, let's look at this one. Is it correct like this? Here you have, of course, you can take out e mu.
Mhm.
This would be e of e sigma z, right? So then this is what is this? You cannot move the e over here, yeah.
No. Wait.
So if you evaluate this thing, this is basically so you have to multiply with the this is a standard normal, right?
Mm-hmm.
So then you have to do you have to complete the square. So this will be z minus sigma over 2 squared 2. Then you have to then you'll cancel off with e of minus sigma squared over 2. Oh, okay, the sigma, sorry, this sigma is, what is it? Okay, that's the variance, right? Yeah, so then this part here will be, I think you will get something like this. This is something like, you know the moment generating function?
Yes.
Yeah, if you recall the what's the moment generating function of the normal? With mean mu and sigma square. It's e of mu plus t square sigma square over 2, right? So basically here, since this is a z, so this will be 0. So you're taking that's 0, that's 1, and your sigma here basically is your t. So that's right lah. You get this one. I think this is a plus. It's a plus. Okay.
Mm.
So basically, then you have E of these times something like this.
Okay.
Okay, just have to check the algebra. I think this should be a plus. So just work out the algebra. Okay.
Okay. I'll correct it.
Uh-huh. So it is actually not it doesn't actually disappear. Okay,
Okay.
so I'm going to look at the third part. Yeah.
Should I stop the?
Okay, just stop presenting.
Okay. Thank you.
Thank you. Okay, so this is the part about the third part, right? If x1, x2, xn are IID log normal with mu and sigma square as the parameters, show that P of max larger than n is as this form, yeah, E of 2 mu plus sigma square over 2. Okay. So basically, from what we know is we know this thing, right? So basically, this is some kind of a complement. So we start with this, right? Because you know you can make progress here. So basically, this is just everything being less than or equals to n, right? So since they are ID, so you can just take one of them. All right. And this is basically 1 minus p x1. All right. So are you able to follow up to this point? Start from here because we can construct this equivalent statement, right? Okay, so from here we come to this point, and then here we use complementation. Okay, is it okay?
Yes.
Right, so then after that, what can we do? Okay, remember your x, right, is equal to E of mu plus sigma z, right? So when you make a statement, okay, let's work with this statement first. Okay, now let's keep this aside. Let's put aside first. Put aside. Let's look at this part, right? So since your x is of this form, so you can write it like this, right? Okay. So so therefore you take log, you will get mu plus does it work? Well, let me see this part here. Okay, let us keep this question for aside for a while. I think I need to. Okay, let's keep it aside first. There's a bit of complexity here that I need to work out. Okay, never mind. Just keep it aside first. Okay, I'll get back to you later about this part. Okay, so okay, let's move on to question 3.
Hello. Hi, doctor.
Hello.
Can you see my screen now?
Yes, I can.
So for problem 3, the question is, suppose x is a uniform random variable of interval 0 to 1. So the question A, we need to show that negative log x has an exponential distribution with mean 1. Then I let y equals to negative log x. So y greater than 0. Then if x greater than 0, then fyx equals to this one. Then p negative log x less than x. And then p log x greater than or equals to negative x equals to this one. Equivalent to 1 minus p x less than and equals to e negative x. And then 1 minus fx e negative x. So we taking the derivative and then we get fyx equals to negative fx e negative x times negative e negative x by using the chain rule. So since fxx equals to 1, x within 0 to 1, this gives f y x equals to e negative x, or y is exponential with mean 1. So that one for question A. For question B, for the question B, I need to show that the expectation of the product of a unique random variable of 0, 1 and exponential random variable with mean 1 is between 0 and SIT3001. But I didn't manage to prove this one.
Can you just just go ahead.
Okay, then I let x uniform distribution 0, 1 and y is exponential with mean 1. So I try by using Swatch inequalities. So expected of xy less than the square root expected, this one. And then I expand becomes this one. And then I change with the value using the distribution mean and variance. Then I cut it and become like this.
Okay. Okay, let's go back to the first part.
This one.
Yeah, okay. So this is correct, but just for notation. So since you use big Y already, so big Y, so you go with the small y, yeah.
Okay.
This is small y, small y. So then basically, basically these are all small y's, right? Okay.
Okay.
So basically, you don't actually. So okay. So since your x is a uniform, right? So in fact, you don't need this because up to here, since it's uniform, so it will be e of minus y. So you have this area under the curve, right? Because your x is uniform, right? So you're larger than or equals to e of minus x. So it's this rectangle. So this rectangle is very clearly 1 minus e of minus y. Okay. So then that's your distribution function. Therefore, your f of y is equal to e of minus y. Y is greater than 0. Okay, because since your x is running between 0 and infinity, so minus log of that will run between 0 to infinity. Okay.
Okay.
Okay. So yeah, this is actually quite. You don't need all these extra things. Up to this point is okay already, right? Yeah. Okay. So then the next part. Part B. Okay. Part B actually actually what you did is not wrong because what you got is actually a tighter bound. This bound is actually tighter than this bound. Did you notice?
Yes, sir.
So if you calculate this value, this is about
0.7 something.
0.7 what?
Something. Not sure. 0.7 something.
To calculate it.
0.7887.
Okay. This one 0.816.
Yeah.
So basically, this is correct because as long as you show something that is, you just need to show that it's between these two values, right?
Yeah.
Here you are showing that the question asks you to show that it's between 0 to square root of 2 over 3. What you did was you show that it's like this. This is definitely correct, right? Because it's this bound is in fact tighter than this bound, right? So yeah, so because the way of you working here is actually it's, let me see, this is if you use absolute, okay, up to this point is okay. So and then this part here, okay, let's look at it carefully. So you have E of x, y minus x minus y over 2 plus 1 over 2. So, okay, so I think the problem may be that you cannot base, since this is a, okay, I think that this may be a bit problematic to show, because what you did here, I think I just noticed it, you move the expectation sign inside. And then you somehow kind of like yeah, then somehow you kind of like ignore the expectation. Sorry, you can somehow kind of like ignore the absolute notation here. So this will cause some problems, yeah. Okay. So maybe up to this point is okay, but after that you'll find that this part is actually very questionable, right? Because simply it's because you can't move the expectation operation inside the absolute function. Yeah.
Okay.
Okay. So let me get okay. So let me show how to do this.
Okay. Thank you.
Okay, so your x is uniform, and let's say your y is exponential 1, right? So you have the Schwarz inequality says the following, right? Okay. So now, if you what Izati did just now was she kind of like subtracted. So she did a transformation. She subtracted. Okay. Now once you subtract, okay, it's a good idea, but once you subtract, we don't know, right? Once you subtract, this can be either positive or negative, right? So then you will have to deal with the absolute sign, absolute function there. So now you look at this carefully. This, if you work with them directly, then you know that this absolute sign is actually not. You can remove it because x is basically positive, y is also basically positive, right? So if you work directly with this, then you right, you say since x is positive, y is also positive, therefore this is basically just, okay, taking the absolute has no effect, right? So therefore by Schwarz inequality, okay, the expectation of x times y is bounded by this expectation, okay? And from here, you know that this is, you know that the variance of x is 1 over 12, right? So the second moment is 1 over 12 plus 1 over 2 squared, okay? So this will be 12, what's it, 4, okay? 4 times 3, okay? So you get 1/3, right? So this is 1/3. And how about y squared? Okay, Exponential will mean one. It's so you have exponential function. So the mean is 1 over lambda. The variance is 1 over lambda square. Okay. If with parameter lambda, right? So in this case, your lambda is 1. So basically, it has a mean of 1 and a variance of 1, right? So therefore, its second moment must be 2, right? Because 2 minus 1 squared will give you 1, right? So you get this. So that's all, yeah? You already show the result that the question asked, okay? All right, so the argument is just to note this, yeah? The thing with using Schwarz inequality is that the annoying part is this absolute function, okay? But you can remove it if you notice certain things about your random variables. If they are all on a positive line, then you basically can get rid of the absolute, right? So then it will allow you to find the expectation that you want, okay? Okay, is it clear, Izaki, to you?
Yes, doctor.
Okay. So I think you did some extra steps, which is actually okay. You can try to introduce something, but unfortunately, I think after that, it kind of like gets stuck because your expectation cannot move. It cannot move inside the absolute function, right? Okay, but it's a good try, all right? Okay, so let's move on to the next question. Before we take a break, problem 4.
Good afternoon, doctor. Can you hear me?
Yes, yes. Just
Can
share.
you share my screen first?
Okay.
Doctor, okay. Can you see my screen?
Yes.
All right. So problem 4, suppose that xn has a normal distribution with mean mu and variance sigma square over n. So I have to show that the probability of absolute xn minus mu greater than epsilon converge to 0 as n approaches to infinity. So recall the Chebyshev inequality. We have the probability of absolute x minus mu greater than alpha is actually less than or equal to the variance or variance of x over alpha squared. So I applied the Chebyshev inequality. We have the probability of absolute xn minus mu greater than epsilon is less than or equal to variance of xn. So the variance of xn is given, which is sigma square over n. So I substitute into this. We have sigma square over n epsilon square. So since the n is in the denominator, we know that as it becomes to approach to infinity, it will become 0 or converge to 0. So the limit of n approach to infinity of the probability is converge to 0 as n approach to infinity. That's all.
Yeah, okay. So yeah, so I think this is correct, but I usually just like to annotate it. Okay, let me just annotate. So I usually just like to, I mean, like, although it's implicit that of course your probability must be more than or equal to 0, but for I always like to put on the left hand side this thing, and then there's the right hand side, right? So basically then yeah, so which means that you have this probability here, right? Is actually bounded by this guy, and as your n increases, it will start to shrink, right? Correct. This is its bound, right? This is the upper bound, right? So the upper bound will keep shrinking as your n increases, right? Until it basically cannot go out of 0, right? That's why your limit is equal to 0. Okay. Right? Is it clear?
Yes, doctor.
Okay. So yeah. So this is just an exercise in applying Chebyshev's inequality. So the only thing you need to know is the variance of this. So your xn is a sequence of random variables, right? Okay, so you just need to know its variance, and its variance has to be finite. If it's not finite, then it doesn't apply. Okay, so like for example, you cannot talk about Chebyshev's inequality for Cauchy distribution because its variance is not finite. Okay, but otherwise, for distributions with finite variance, then you will be able to use this result. Okay. Okay. Thank you.
All right, thank you, Doctor.
So let's take a 10-minute break now. Right, then I come back to solve the remaining problems. Okay, so welcome back. Okay, so we will present, we'll look at problem number 5 now. Okay, so let's present problem number 5.
Doctor, can you see my screen?
Yes, yes.
So for question number 5, the question asks us to show that first lim sub an complement is equal to in bracket of lim in an, and the second one is lim in anc is equal to in bracket of lim sub anc. So first, by definition from De Morgan's law, we know that lim sub an is equal to this set, which is intersection of union an and lim in an, is equal to this set, which is union of intersection of an. So for the question, for the first question, lim n sub anc is equal to this set, and then we put a bracket for both sides, and after this the sign which will change, and we know that it is equal to lim in a and c, and it is shown. And for the second one, lim in a and complement is equal to this set, and we also put the bracket for both sides, and we can show it equal to lim sub a and complement.
Okay, just hang on there, yeah. I want to annotate your screen. Okay, first thing is this notation, right? You have to write it out properly, yeah.
Oh, okay.
Because if you just write like this, it's unclear what is going on, and this indexing is actually not correct.
Oh, okay, then.
Okay, so you have to write it out correctly like this. Then, okay, then here, this should be lim sub of A and C should be, so this should be a, see, this is one thing, right? So it should be like this. All right? So you didn't put it here. Because if you go by definition, this is one thing, right?
Yeah.
One set. So you just replace AN with ANC, right?
Yeah.
Okay. So after that, okay, so you have this. Therefore, if you take lim sub A and C, you complement this thing. So it's basically complementing the whole thing, right? Okay, you complement this whole thing, right? Okay, this is what you did here, but there's a C inside, right?
Oh, okay.
It's left out. So once you got this one, then you apply De Morgan's law, right? So this intersection will become a union, and then basically you have so the complement will come to this part, right? You come into this part, right? Okay, the complementation will come into this part here. So then you apply, so you complement that, so you get intersection AK, K equals to N to this. And then this complement flips the union operation, and it flips here, right? So the CC disappears, right? Okay, so you get this. Okay, so here it is doubtful, okay, unclear. So only here, so for this day you come to here, and this one by definition, this is the lim So this is lim inf of a k, right? Sorry, an. Lim of an, agree?
Yeah.
So then you remove the complementation sign by complementing both sides. Therefore, because lim sup of this complement is equal to that, so therefore your lim sup an complement is equal to lim inf an complement, right? Okay. So the point is you have to show until this part, and then you remove the complementation by complementing both parts, both sides. So then you will get this. You will show this identity, right? And then the other part. So this one again, you apply the definition. So your lim inf of an c will be union intersect a k c. Okay. So then you again, since you see this complementation is coming out, so you take complement. Okay, so then you complement this thing. And it will flip this union to intersection. And then this will come here, so the intersection will flip. And the CC will cancel, right? Okay. So then you complement again. So this one by definition is lim sup of an. Okay. So then you complement both sides. So this complement will go away. It will come over here, right? Then you show part 2. Okay.
Okay.
So be careful. So this one, your students, you must write it out properly like this. Okay. Because otherwise, what is happening here? We don't know what is happening here. What is happening here? So what is being intersected? What is being taking union? Yeah, not unclear. Yeah. Okay. Right. Okay. Thank you, Shaswani.
Thank you.
Then the next question, problem 6.
I'm the one who doing question 6.
Okay. Eugene.
So can you see my screen?
Okay.
So basically, question asks us to find the lim sup an and lim in af an. So basically, the first thing I did is I sketched out the graph. And question given that a1 is xy, where x is in between 0 and 2, and y is in between 0 and 1. And a2 is basically 90-degree rotation at the point 0.5 and 0.5. So this is a1, and this is a2, and this is a3, a4, and when it comes to a5, it will basically change, rotate back to a1, and this is a cycle. So as we know that the formula for lim sup an is the intersection of all union. I will get that I will get the cross is the region of lim sup an, while for lim in af an is known that it is the intersection of all. It is the union of all intersection. So we are basically getting the middle box as the points for lim in an. So when we are looking for the probability of lim sup an, it's basically the region of, I call this region S1. So it's basically the area of S1 over the area of the 4 times 4 square. So I'm getting the value of 5/16. While for probability of lim in an, it's basically the area of A2. This is my S2 over the area of the 4 times 4 square. So I'm getting 1/16.
Okay. Okay. Very good. So you solve the problem so the problem becomes easy when you understand the geometry, right?
Yeah.
Okay, let's go back just to go through the thing with the students. Annotate. Okay. So basically, first you sketch out the set, right? So this is your A1. So this is a rectangle, and you're rotating at this point, right? So
Hey, sorry. I'm sorry.
so rotation. So you can kind of like imagine that you stick a pin here, and then you kind of like turn the, okay. If you have different points of rotation, the geometry will look different, right? But so for this case, I pin it here in 0.5 pin here. So when I rotate, right? So you rotate, so it will kind of like 90 degrees. So this guy will come here. Okay. So this rectangle will move here. That will be A2. Then it will come down here. Another rotation 90 degrees. And 90 degrees. I mean, like you can generate all kinds of geometry. Like you can rotate it 45 degrees or whatever, right? That you can cut. There are a lot of possible extensions, right? But I just wanted to illustrate a general idea. So basically, yeah, and then you are right. After A4, so A1, A2, A3, A4 are different, but A5, A6, since you are rotating, right? So it kind of like repeats itself. So yeah, so that's it, right? Your A5 is basically the same as your A1 and so on. So when you talk about lim sup of AN, right? So lim sup of AN, you first take union, right? You take union of all the possible sets. So you can take union A1, A2, A3, A4, and so on. So the first time you take it, you already get the cross, right? You already get this geometry, right? If you take start from A2, you will get A2, A3, A4, but then A5 you will come back here, right? So you still get the same geometry, right? So no matter where you start, right, you will keep on getting the same geometry, right? And therefore, when you intersect all the unions, right, they are the same, right? Because so all these sets are the same. So you take intersection, it's still just this cross here, okay? So I mean, I do this because it's basically this cross is made out of rectangles, right? So it's very easy to compute, okay? So then you define the geometry for lim sup. Lim inf, basically you take intersection first, right? So you take intersection. So every one of these rectangles, when you take intersection, you will end up with the middle box here, okay? So you don't. So they only share the common part, which is the middle box. And then when you take union of all the intersection, it's still this small box here, right? Therefore, your lim inf is basically the square, right, in the middle, okay? So then finding the probability will be easy, right? Because you basically just consider, so I have it's going from -2, okay, so it's like this, right? Yeah. So the total area is like, you kind of like imagine that you're randomly shooting on this board, right? Okay. So the chance that you basically hit those geometries will be proportional to the area covered by those geometries. Okay. So that will be easy lah, right? Your total area is how long is it? It's a square, right? 16, right?
Yes.
-2 to 2 times -2 to 2. So length is 4, so the total area is 16. So then basically you divide the area of your geometry by 16, all right? Then you can get. Okay. So what do you get?
5/16 because there are 5 boxes there.
1, 2, 3, 4. Yeah, 5 boxes. Then the other one is just 1 box lah. Okay, great.
Okay, thank you, doctor.
Okay, thank you. So you can see this kind of lim sup, lim inf thing is actually not. It's not a very scary thing because it basically just represents a set, right? So in particular settings, they can have a very simple geometrical representation. So yeah, that's the whole point, right? Just to show you that, well, sometimes of course they can be abstract, but sometimes they are basically just geometrical objects. Okay. All right. Okay. So move on to problem 7.
Yeah, it's me.
Okay.
Yeah, I'm looking for. Can you see me? Can you see my screen?
Yeah. Yes.
Okay, so my question is, I need to show that if the summation of PAN converge, then the lim sup PAN is equal to 0. And I separate it into 2 steps. First, we show that the lim sup PAN is smaller than P lim sup AN by the Fettel's lemma. And for the second step, we will just apply the first Borel-Cantelli lemma, and then we will finish our proof. So for the first Fettel's lemma, we know that the lim actually for the Fettel's lemma, it actually can separate into 2 stages. But this is the first stage, and then this is the second stage. For the first stage, we know that the lim infinite AN is actually equal to something like this. And then we just let this thing into the BK. This is what I'm doing here. And then we know that the BK is the increasing sequence to limit infinite AN. And because the BK is the subset of BN, so because the BK is a subset of AN, so the probability of BN of BK will be smaller than probability of AN. Or we say that the PBK is smaller than the infinite of PAN. So for this 1.1 and 1.2, we can make the P limit infinite NAN to be smaller than limit infinite PAN. And then because the AN is a sequence of the event, so we say that the transpose of AN is also a sequence of the event. It's something like we say that they share the same characteristic. So because we just let the AN to become the ANC. And then we negative it, and then we plus 1, so we will get this. So now for the left-hand side, we do some, for the left-hand side, we know that the limit infinite ANC is actually something like this one. And then we apply the De Morgan's law that just now the doctor explained in the question 5. We will get the lim sup NAN bracket transpose. And then we can see that this thing is actually something like 1 minus PAC. So we just let all of this to become P lim sup AN. And then for the right-hand side, actually from this step, to be honest, from this step to this step, I personally don't know how it works. I just searched it from internet, so it says like this. And then for the second step to this result, we still apply PA equal to 1 minus PAC. Okay, so for left-hand side, we get this, and then right-hand side, we get this. And then we interchange them, then we get this. In the first step, we will get this result. The lim sup and PAN is smaller than P lim sup AN. As the hint asks us to do so. So I do this. So for the second step, we apply the Borel-Cantelli lemma, which is I didn't further explain this because this one is explained in the lecture. So the first Borel-Cantelli lemma states that as the summation of PAN converges, then the P lim sup AN is equal to 0. So because we already know that lim sup PAN is smaller than P lim sup AN, and this one is equal to 0, so we can say that the lim sup PAN is actually smaller than 0. And because the probability is the non-negative, so we say that the lim sup PAN is equal to 0. So that's all.
Okay, Xinjie, but you used the result that I did not teach in the class.
Yeah, I'm not really sure whether
we actually you don't need to use, because otherwise there will be we generally don't use results that I know this for Toast lemma is one of those things, but we're not using it. So
Okay.
So if you use this argument, it will be difficult to follow, yeah, by other people.
Okay.
Never mind. Okay, so let me just go through it with everyone, right?
Okay, sure. So I stop my sharing or I stop sharing?
You can stop the sharing. Okay. So the question is, it says, show that if some of these converges, then lim sub PAN is equal to 0, right? And what was the hint given? Show that lim sub PAN is bounded by P lim sub AN. Then use Borel-Cantelli lemma first. Okay. Okay, so basically this is, you recognize this as the Borel-Cantelli lemma condition, right?
Yeah.
Condition, right? So okay, it wants to make some kind of in the Borel-Cantelli lemma, it basically just says P of lim sub, right? It doesn't say anything about the lim sub P of. I mean, like Borel-Cantelli lemma one says that if this converges, then P of lim sub AN is equal to 0. This is what it says, right? Borel-Cantelli lemma.
Yeah.
It seems like in this question, it's like you can kind of like move this P inside you, and it also be true, you know. This is the point of the question. Borel-Cantelli lemma 1 says that if this condition is true, then we have this result. Okay, but then here we prove that actually this is also true. That in fact it seems like if you take out the lim sub, you put the P inside together with the AN, it will also be true, right? So we want to show this. Okay. Now, okay, so first show this lim sub is bounded by this. Okay. Now, first thing we note the following. Okay. So what is this? This is okay. This is the supremum. Okay. So you have when you have a PAK, this is a sequence of probability values, right? For the sets A, AK equals to N, N plus 1, and so on, right? So this is the supremum of a set, okay? The supremum of this set is definitely bounded by P of union AK, K from N to infinity. Agree?
Mm-hmm.
The reason is very simple. Your P, so this is your PAK, right? So it will be basically, so this is your, let's say your AN plus 1, AN plus 2, whatever, right? And so on. Each of these will have a probability. Let's say a probability is like this. Doesn't matter, it can be like anything, right? Okay, you are finding the supremum in among this set, right? So for example, so it will be basically just one of these guys, right, will become the supremum. Let's say this guy is the sup. Okay, this guy here, it's so even the AK with the highest probability, right? It cannot be larger than the probability of, if you take union of all these sets first, you take their union, they will become a large set, right? Then you apply a probability measure on it. Definitely it cannot go out, right? Okay, is it clear to everyone that this is true? This is a sequence of probability values. You are taking the supremum among them, right? So it's only one guy, right? It's only one of the sets. But here you are taking the union of all the sets first before applying the probability measure. So definitely we know that this has to be true, okay? Because your individual values are, you take even the largest among them cannot go out of this probability of the union of their sets, okay? So this is, once we establish this, then we can talk about the next thing. So you take limit on both sides, yeah? Take limit on both sides, so you will get okay, you get this, right? So basically your left hand side is basically just a lim sup of PAN, right? By definition, yeah. So your left hand side is basically P of lim sup, okay? And this one is definitely larger than 0, yeah. Okay. So the right hand side here, this guy here by definition is equal to P of N union AK. Okay, when you take limit of this thing is the same as intersecting all the possible. So because you see, this one, what is happening here is that this is your K, right? You're taking your N to be getting very large, yeah. So you're basically only taking the intersection of the tail. Sorry, you're basically taking the union of the tail events towards the end, right? This is the same as you are intersecting. You keep intersecting this union countably many times. Okay, so you need to make this connection. This is probably the connection that is maybe not so. You have to connect like this. Okay. So once you connected from here, this is basically by definition, this is just a lim sup of AN, right? By definition. Okay. So what do you have now? So now you basically establish the fact that lim sup P of AN is bounded by P of lim sup AN. Okay. So you got this in this bound, right? Then by the first Borel-Cantelli lemma, if this converges, then this is equal to 0, right? So which means this is equal to 0 by first Borel-Cantelli lemma, right? Yeah, because this is the implication from Borel-Cantelli lemma, first one. So once this becomes 0, then you see that your lim sup P of AN is sandwiched between 0 and 0. So therefore, it must be equal to 0. Okay, so this is the idea here is to construct this inequality, and then this bound here you can find from Borel-Cantelli lemma 1, right? So then it implies that this quantity is equal to 0. Okay, so this is the idea, yeah. So now you know that for the first Borel-Cantelli lemma, not only you have this result, but it also implies this result. Okay, the lim sup of PAN is equal to 0. Okay. All right. Okay. So I think yeah, unfortunately, it's taken up all of our time to even talk about this this single tutorial. Yeah. Never mind. So for tutorial 7, you will let me see. Tutorial 7, we will talk about it next week lah. Okay. Okay, we'll talk about it on next Thursday, and also just a little bit more about the characteristic function. Later, I'll post up. So please check the spectrum later in the afternoon today. I'll post a notification in Flock, right, for the continuous assessment 2, right. Please look out for that later in spectrum. Okay. So are there any questions that you want to ask? So for the continuous assessment 2, you have 2 weeks to do it. Yeah. So plenty of time. You can don't worry about the solutions for the other tutorials. I will be posting them one by one in the coming week. Okay, so if there are no more questions, then we will stop here for today. Yeah. Okay.
Sure. Thank you, Doctor.
Thank you, Doctor.
Okay, thanks everyone.
Thank you, Doctor.
Thank you, Doctor.
Yeah, okay, I'm going to end the meeting now. Yeah.